All right, so today we are going to actually delve into three-phase circuit analysis, specifically balanced three-phase circuit analysis. And we are going to establish some ground rules on how this is going to work by looking at a balanced Y-Y system. So let's start with something that looks like this. So we're going to have a Y-connected source. Over here, we are going to have a Y-connected load. Capital B, C, and capital N. And we are going to connect our source to our load using transmission lines. And our lines will have some associated impedance. So I am going to say the impedance of the transmission line for phase A is ZWA. Then we will have ZWB, ZWC, and ZWN. Similarly, I'm going to have specified impedances for my load. So I'm going to call that guy ZYA on the A phase, ZYB on the B phase, and ZYC on the C phase. Okay. So here's our YY system. Now, we are going to be dealing with balanced systems first. So I'm going to very methodically explain exactly what a balanced system is because it is important, okay? So for this circuit to be considered balanced, we need the magnitude of the phase voltages at the source to be equal. Which means the magnitude of VAN is exactly equal to the magnitude of VBN is exactly equal to the magnitude of VCN, we need the phase separation between the phase voltages at the source to be 120 degrees, which means that theta Bn is equal to theta An minus 120 degrees and theta Cn is equal to theta An minus 240 degrees for an ABC or positive phase sequence, and theta Bn is equal to theta An plus 120 degrees and theta Cn is equal to theta An plus 240 degrees for a negative phase sequence. We're going to use positive phase sequence in this class like I've discussed before, but I'm just trying to very methodically go through this. So that balances our source. We need the transmission line impedances to be equal. Oops, that's not how you spell impedance. So ZWA is exactly equal to ZWB is exactly equal to ZWC. And so we'll call these simply Z wire or ZW. I'll probably use Z wire though. Notice here that I have not made mention that the impedance of the neutral conductor has to be the same here, okay? It does not. It can be whatever it needs to be, which if you look at the NEC code, there are specific constraints for the phase wires or the transmission line sizing and all that. But the neutral conductor can be much, much smaller than the transmission lines. The reason for that is we shall see that the neutral line in a balanced system winds up carrying no current whatsoever. It doesn't even physically need to be there technically if your system is perfectly balanced. If your system is unbalanced, the neutral conductor only carries the unbalanced portion, which is typically much, much smaller than the other conductors. So ZWN does not need to be equal, is the only point I'm trying to make here. We'll mathematically prove it momentarily. All right, then our last constraint is that the load impedances are equal, meaning ZYA is exactly equal to ZYB is exactly equal to ZYC. So I'm just going to call this from here on out ZY. Under these four conditions, we have a balanced YY system, okay? So we can really see the advantages of analyzing a balanced YY system if we find the line currents in the system. So I'm going to go up here real quick and define what those line currents are, just so that we're all on the same page. So my line currents are, by definition, the currents flowing through my transmission lines. So I'm going to call this guy IAA. I'm going to call this guy IBB. I'm going to call this guy ICC. And I'm also going to include this guy INN here because we're going to be doing Kirchhoff's current law momentarily, and we're going to have to take that guy into account. One other thing that I am going to do is I'm going to specify a reference node for our analysis, just so things will be a little bit easier. And so I'm going to call the neutral on my source side my reference voltage of 0 volts, okay? So from that, if I apply Kirchhoff's current law, let's look up here real quick. If I apply KCL at the rightmost node, so way over here, what do I have? Nothing too fancy here, right? So my current IAA is flowing in. My current IBB is flowing in. My current ICC is flowing in. My current INN is also flowing in. So if I apply KCL at the rightmost node, I get IAA plus IBB plus ICC plus INN is equal to 0. Now I'm going to use Ohm's law to write these currents in terms of some of my known voltages, okay? So I am going to say that my current IAA is simply this voltage, VAN, the voltage at that node with respect to ground, minus the voltage at this node, V capital N lowercase n, divided by the impedance between those two node points, ZWA divided by ZYA. And I can follow suit for the remainder. And so this is going to give me VAN minus V capital N lowercase n divided by ZWA plus ZYA, VBN minus VNN divided by ZWB plus ZYB, VCN minus VNN over ZWC plus ZYC. And then I have to take into account my neutral current there. So I have INN directed this way. So I'm going to call that minus V capital N lowercase n divided by ZNN. So I'm changing my current to get my subscript on the ends the same as the other things, so I can easily add them together. So instead of having plus here, I should have minus. Sorry. And I realized I messed up the subscripts there. Capital N little n minus V capital N little n divided by ZN, ZWN is equal to 0. If my network is balanced, this will reduce fairly easily, okay? So I will see that V capital N little n divided by the impedance of my neutral conductor will be equal to VAN minus VNN over Z wire plus ZY plus VBN minus V capital N lowercase n. Dang it, I got this one backwards. Over Z wire plus ZY plus VCN minus VNN over Z wire plus ZY. And I can rearrange things, and it leaves me with this relationship. V capital N lowercase n multiplied by 1 over ZWN plus 3 divided by Z wire plus ZY is equal to VAN plus VBN plus VCN all divided by Z wire plus ZY. Now, get your calculators out. This is going to be a real quick calculation, okay? If our source is balanced, then VBN is the exact same thing as VAN, but shifted by 120 degrees, positive or negative, depending on if we have a positive phase sequence or a negative phase sequence. Similarly, VCN is just VAN shifted by 240 degrees. So get on your calculators and add the following complex numbers. 1 angle 0 plus 1 angle negative 120 plus 1 angle negative 240. Because these are the relationships by which the voltages are related. When you add them all together, what do you get? 0. So if I add all of the voltages in my system together at the source, they equal 0. Makes perfect sense. So what that means is that I have 0 in my numerator right here, right? What does this imply? VAN plus VBN plus VCN equals 0 is because my source is balanced. But that means the left-hand side of this guy is also 0. Now 1 over my wire impedance for my neutral line plus 3 over the total impedance seen downstream, that's gonna not be 0. So this implies that the voltage drop over my neutral conductor is always 0 for a balanced 3-phase system, okay? Since the voltage drop over it is always 0, that is critically important to our analysis, okay? Voltage drop over is 0, so it's behaving as if it were a short circuit, right? So if the voltage drop over is 0, it acts like a short circuit. Even though we know it has some finite impedance, it's behaving as if it were a short circuit because our system is balanced. So I'm going to put an arrow here. V capital N lowercase n must be 0 volts. All right, so using this information, what's the current through my neutral conductor? Well, it should be negative V capital N lowercase n divided by ZWN, where the negative sign is coming from the fact that I'm using lowercase, uppercase subscripts on the left-hand side of the equal sign and uppercase, lowercase subscripts on the right-hand side of the equal sign. I know all this bookkeeping is going to get awful, but we're very, very quickly going to approach a point where it's going to be really trivial. So I have my current is equal to -0 divided by some finite number. So what's my neutral conductor current? It's 0. So this is really interesting as well. Okay. My neutral conductor in a balanced three-phase system acts like both an open circuit and a short circuit simultaneously. This may seem wonky, but it's actually going to make the circuit analysis that we're going to be doing very, very much simpler. Okay. Let's look at our other line currents. All right. So let's look at IAA explicitly, the line current through the A phase of our transmission line. So we had VAN minus VNN divided by ZWA plus ZYA. Using the fact that we have a balanced system and recognizing that VNN is equal to 0, this reduces to VAN divided by Z wire plus ZY. Nothing super important right here, but let's look at the current through our B phase. VBN minus VNN divided by ZWA, ZWB plus ZYB becomes VBN over Z wire plus ZY, which I can rewrite as VAN over Z wire plus ZY multiplied by a factor of 1 angle. I'm going to say negative 120 degrees here because I'm using a positive phase sequence, but we could just as easily say it's positive 120 degrees for a negative phase sequence. So what does this tell me? My line currents are going to be exactly 120 degrees out of phase with each other as well for a balanced system. So from this, I can easily see then that ICC is going to be VAN divided by Z wire plus ZY times 1 angle negative 240 degrees. Okay, so we found our line currents, and we have now recognized that because our system is balanced, all of our line currents are exactly 120 degrees out of phase, just like our source voltages. What does this tell us about literally everything else in the system? Well, let's scroll back up here and look at this, recognizing that our line currents that I've indicated in red are 120 degrees out of phase with each other. What about the phase currents through the source? Are they going to be 120 degrees out of phase with each other? They have to be. They're in series with our transmission line currents. Similarly, the line currents at the load, or excuse me, the phase currents at the load are going to be 120 degrees out of phase with each other. That means that the phase voltages at the load are going to be 120 degrees out of phase with each other. That means the line voltages at the load are going to be 120 degrees out of phase with each other. So when we have a balanced three-phase system, we ever actually only need to solve for what's happening in one phase of the system. Everything else we can assume is shifted by plus or minus 120 degrees or plus or minus 140 degrees, depending on both our phase, or 240 degrees, depending on both our phase sequence and which particular phase we are looking at. So that brings us to our simplified model, which is called the single phase equivalent circuit. All right, so in our single phase equivalent circuit, we are going to be exploiting the fact that VNN and INN are both 0. So it does not matter what the actual impedance of the neutral conductor is, we are going to treat it as a short circuit. So for any balanced three-phase circuit, or any balanced three-phase YY circuit specifically, we can actually split it up into 3 single-phase circuits, okay? So for the A phase, that's going to look something like this. Here's A, here's lowercase n. Here's Z wire. Here's capital A. Here's ZY. Here's capital N. Short circuit. For the B phase, here's our circuit. And for the C phase, it's going to be the exact same thing, except we're going to have capital or lowercase c and capital C where appropriate. What's the only difference between these? The fact that the voltages are 120 degrees out of phase, right? So all of the information is taken care of. What this means is that for any balanced YY circuit, all we have to do is analyze this easy peasy single loop circuit, and we can get all of the information about it that we want. We can get all of the phase voltages, all of the line voltages, all of the phase currents, all the line currents. Everything is found within this joke of a circuit that at this point you guys can analyze in your sleep effectively. You may not be able to do the calculation in your sleep, but the analysis is ridiculously simple. So let's work a quick example problem just to show this before we move along to something else, okay? So let's say I have the following description. This is going to be in the style of what your next several homeworks are going to be like. A positive phase sequence balanced three-phase Y-connected source supplies power to a balanced Y-connected load. The magnitude of the line voltage is 208 volts RMS. If the load impedance per phase is 36 plus J 12 ohms, determine the line currents if the angle for VAN is 0 degrees. All right, this is the style of the problems that I'm going to be asking you. There is no provided circuit diagram. I'm literally just telling you how things are connected. So here we are told that we have a Y-connected source and a Y-connected load. We are given no mention whatsoever of transmission line impedances, so we are going to assume that they are 0. Okay, if we're not told what they are, the best we can do is say they're short circuits, all right? So if I wanted to draw our circuit based on the problem statement, it would look something like this. Here's A, B, C, and N. Here's VAB, which we do not know. This can be VAN, which we do not know. VBN, which we also do not know. VCN, which we don't know. My transmission lines, I'm approximating as short circuits because we were not given an impedance for them. And then here are my loads. Like so. The information that we are provided is this. The magnitude, sorry, VAB, of our line voltage is 208 volts RMS. We could do the same thing for the line voltage between B and C, but we don't really need anything else. And I would argue that that is enough information for us to determine our line currents, recognizing that this is a balanced three-phase system. So I'm going to just identify my line currents real quick, doing them in red to let you guys know this is explicitly what our goal for solving this guy is. Now, let us postulate. Okay. So in order to apply our single phase equivalent circuit, we need to know what the phase voltage at our source is, right? We are given our line voltage. Does anybody have any thoughts whatsoever on how we might approach using the fact that we have the magnitude of our line voltages to get our phase voltage? Yes, sir.
The magnitude of VCA and VB, or VA and VB are the same, right?
So the magnitude of VAB is equal to the magnitude of VBC, which is also equal to the magnitude of VCA. Because we have a balanced three-phase system, we could fairly easily determine that VBC lags VAB by 120 degrees and VCA lags VAB by 240 degrees, but we don't know what the actual phase angle of AB is because we're only given the magnitude. The only phase angle that we know for sure is the phase angle of VAN, our phase voltage, not our line voltage. Yes?
So I guess if VAB equals VB minus VA, VA like
I think I get what you are, I think I understand what you are getting at. Did I write VAB here instead of VAN? Sorry. That might be confusing if I did, so let me make sure that that says VAN. Okay, so I think I understand what you were saying. I'm going to explain it in a slightly different fashion. I can write a Kirchhoff's current law loop around this little guy right here, because while I don't know what the magnitude of these guys are, I do know what their phase angle relationship is. So I can say, starting at the bottom left-hand corner, negative VAN plus VAB plus VBN is equal to 0, right? KVL around that loop. I'm going to rearrange things slightly. So I'm going to say that VAB is VAN minus VBN, which I believe is what you were mentioning, Chris. I can rewrite this a little bit further and say that this is VAN multiplied by 1 angle 0 degrees minus 1 angle negative 120 degrees because of my positive phase sequence, which means I have VAN multiplied by all means, double check my math on this, square root of 3 angle positive the heck just happened? Positive 30 degrees. Now it has been 6 months since I've done this. So I'm just going to make sure real quick that it is supposed to be positive 30 degrees. Yep, 1 minus 1 angle negative 120. Convert it into, yep, root 3 angle positive 30 degrees. Okay. So based on what I know then, VAN is simply the magnitude of VAB divided by the square root of 3 with an angle of 0 degrees, and 208 divided by square root of 3 is, 120.089 angle 0 degrees volts RMS. Typically speaking, we just call that 120. So if you go, I think even if you go into my office, actually, there's a 3-phase panel on my wall. And it says something like 208/120Y. It's 208 volts line to line, 120 volts if you consider it to be a Y configuration. That's how transformers are rated and all that kind of stuff. If you peek in, I do not suggest you peek into any of the panels in any of the buildings here on campus because I don't want to get sued if you do it and hurt yourself. But if you were to do so without my consent in any way, shape, or form, you would see little nameplates all over the place that say things like that. Because our university, and particularly Ethan Hall, is serviced by 3-phase power because we have our power lab that runs 3-phase motors and all that kind of good stuff. Now that we have this relationship for VAN, it's fairly straightforward to apply our single-phase equivalent circuit. But I want us to pay attention to something real quick here, okay? We have just developed a relationship for converting from line voltages to phase voltages for a Y-connected source, okay? And similarly, if we do this backwards, we can see that multiplying a phase voltage by this factor of square root 3 angle 30 degrees gives us our line voltage. So we can go back and forth between line voltages and phase voltages for a Y-connected source now. And as it turns out, it also works out for Y-connected loads because it has to. It's a balanced system where everything is related by that 120-degree phase shift. So we're making headway towards analyzing other types of circuits. You just may not even realize it yet. All right, so from this information, our single-phase equivalent circuit looks like this. Here's our phase current, excuse me, our line current, IAA, where by inspection, IAA is simply VAN divided by 36 plus J12 ohms. So let's see, 120. Oh, I have it written down. I'll just do this thing. 3.165. No, go away. Go away. Go away. Angle negative 18.435 degrees, amps RMS. If I were interested in the line current IBB, which I am because I want all three of them, do I need to bother figuring out a single phase equivalent circuit for the B phase and doing math and all that kind of crap? Exactly right. So I just do what I have here and then subtract 120 degrees from it, and I don't need to do any more work than that. So that would be 3.165 angle negative 138.435, and ICC. Did I bother writing all of them down? Yes. 3.165, angle negative 258.435 degrees. That's RMS. Would this circuit be any more difficult if we had included a line impedance for our transmission line? Not really. We would have just had a different number here in the denominator, but other than that, it's easy. So, analyzing YY circuits using a single phase equivalent circuit makes three-phase circuit analysis ludicrously simple. Can we agree on that statement? The only thing that I could do to make this more complex would be to put an impedance right here, which is still a boring single loop circuit, which besides the fact that it has complex numbers in it, is something that we analyze on like the second day of circuits 1. Yes, sir. So because of the impedance on the neutral line, it's a balanced system. It doesn't matter what the impedance is, or even if it actually exists, meaning there may not physically be a wire connecting the neutral terminal on the source to the neutral terminal on the load. We can treat it as a short circuit because it is a balanced system. So for a balanced system, it does not matter what the neutral impedance is. It's always the short circuit. All right, so there are multiple different ways to approach the remaining types of circuits that we're going to see. So we've got YY fairly on lockdown now. So we could look at Y delta, delta Y, and delta delta. Numerous different ways. The way that I prefer to do it is by introducing transformations so that we can make a delta connected source look like a Y connected source, and we could make a delta connected load look like a Y connected load, so that we can convert any of the 4 different permutations to a YY circuit, which we can analyze using this joke of a single phase equivalent circuit and get everything we need extraordinarily easily. So let's come out of our example problem here and talk about our source transformations. There we go. All right, so if we have a Y connected voltage source, let's call this guy A, B, C, and neutral, which makes this voltage VAN, this voltage VBN, and this voltage VCN. Then we can find our line voltages to be VAB, VBC, and VCA, right? Just the voltage between those terminals. So nothing more than simple terminology here. Well, if VAN is equal to some magnitude, I'm going to call it VP, standing for phase voltage, angle 0 degrees, and VBN is just that same VP with an angle of negative 120, and VCN is VP with an angle of negative 240. Then our line voltages, VAB is just VAN multiplied by root 3 angle 30 degrees. From our previous example where we converted back the other direction, which I'm going to call this VL for line voltage, angle 30 degrees. BBC is then just going to be VL angle negative 90 degrees. VBN root 3 angle 30 degrees, which is VL angle minus 90, and VCA is VCN root 3 angle 30, VL angle minus 210 degrees. There we go. So I can convert from my phase voltages in my Y connected source to my line voltages in my Y connected source, right? Well, if I know my line voltages, I can immediately transform from a Y into a delta just by using that simple conversion factor of multiplying each of my phase voltages times a factor of square root of 3 angle 30 degrees, right? So what I'm arguing is if I have I can now convert to this guy. VAB, VBC, VCA by simply multiplying by root 3 angle 30. I can go from a Y to a delta fairly trivially, right? Well, it stands to reason then that I should be able to go from a delta to a Y by doing the opposite operation, meaning instead of multiplying by square root of 3 angle 30, I divide by square root of 3 angle 30, or I could take it as multiplying by 1 over the square root of 3 angle negative 30 degrees. I'm going to use the multiplication factor so that we're always multiplying so that it's not confusing when you're remembering whether you're supposed to multiply or divide. So to go in the opposite direction, so when we go from Y to delta, we multiply by square root of 3 angle 30. when we go from delta to y, we multiply by 1 over root 3 angle negative 30 degrees. And we now know how to transform our balanced sources from delta to y and y to delta, based on that very simple relationship we stumbled upon working the last example problem. Now, let's talk, any questions on that before we move on to transformation between balanced loads? Hopefully it's fairly straightforward. You go from y to delta, you multiply by root 3 angle 30. You go from delta to y, you multiply by 1 over root 3 angle negative 30. It's just that simple. Doesn't matter if that's a source or a load if you're doing those voltages. All right, transformation between balanced loads. So let's say that I have A, B, C. So I have a Y connected load like so, and I have a delta connected load like so. So let's call this Z delta A. Z delta B. And Z delta C. I want to convert between these guys. I'm going to have to do what's called a delta Y or Y delta transformation, which if you recall way back on homework 1, the first problem, the only way to determine the impedance of that network directly was doing this. And I mentioned it in the hint. I told you guys to give it a Google. We're going to walk through it a little bit more formulaically here. So the impedances seen between terminals A and B capital letters because it's a load, my apologies. ZYA in series with ZYB, right? So if I'm looking between terminals A and B of my Y connected load, I see ZYA in series with ZYB. Nothing too wild or crazy there. And the impedances, or the impedance, I guess, of the delta load is, so let's take a look at this guy real quick. And I got to make sure that this is clearly saying ZAB. All right. So I see Z delta A in parallel with the series combination of Z delta B plus Z delta C. So Z delta A multiplied by Z delta B plus Z delta C divided by ZA plus ZB plus ZC. I'm going to set these two guys equal to each other. How I'm going to convert between them is I have to say that the impedance seen between the A terminal and B terminal is the same. ZYA plus ZYB is equal to Z delta A, Z delta B plus Z delta C divided by Z delta A plus Z delta B plus Z delta C. And if I were to repeat this process for the other terminal pairs, I would get ZYB plus ZYC is equal to Z delta B, Z delta A plus Z delta C over Z delta A plus Z delta B plus Z delta C, and ZYC plus ZYA looks like Z delta C multiplied by Z delta A plus Z delta B over Z delta A plus Z delta B plus Z delta C. So I have a system of 3 equations and 3 unknowns, and what I mean by that is if I know what the Y impedances are, then the delta impedances are the unknowns. If I know what the delta impedances are, then the Y impedances are the unknowns. So I can solve these guys. So my Y delta transformation I get Z delta A is equal to ZYA plus, ZYA multiplied by ZYB plus ZYB multiplied by ZYC plus ZYC multiplied by ZYA, all divided by ZYA. Z delta B in terms of my Y impedances is ZYA, ZYB plus ZYB, ZYC plus ZYC, ZYA, all divided by ZYB. And lastly, Z delta C, same numerator, ZYA, ZYB plus ZYB, ZYC plus ZYC, ZYA, all divided by ZYC. All right, so that's a lot of junk to remember. But we have a balanced load. That's the whole purpose of this. So in a balanced load, ZYA is exactly equal to ZYB is exactly equal to ZYC. So what does this reduce to? So I have 3zy squared divided by zy is just 3zy. So z delta is equal to simply 3zy. So if I want to convert from a y to a delta and I have a balanced load, I simply multiply my load impedance by 3, and that gives me the delta configuration. What do you think is going to happen when I go the other direction? I divide by 3, or I multiply by a factor of 1/3. So I'm just going to state that explicitly. Zy is 1/3 multiplied by z delta. And so I'm going to come back up here and draw my little symbol thingy. So z delta is 3zy. Zy is 1/3 z delta. And there we go. All right. So I now have a means by which to convert any configuration of a three-phase load connected to a three-phase source, a three-phase source connected to a three-phase load into a YY circuit, which I can then analyze using my single-phase equivalent circuit. So when we get back on next Friday, we will spend a day working numerical examples of increasing difficulty, meaning I'm going to start putting loads in parallel with other loads. So a Y load in parallel with a Z load and blah, 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 that kind of stuff. But for the most part, we have three-phase circuit analysis under wraps. Okay, it's this simple. If you can convert it to a YY system, do so, make your life easy, do the simple circuit analysis. Yeah, so when we come back next Friday, we'll talk about just doing some numerical analysis, and we'll wind up developing relationships between phase currents and line currents through that. All right, you guys have a good Mardi Gras break. See you in a week.